a second or so just to clarify and see if I can sort this out. Talk to me. Is my sound still not clear, or maybe it could be someone else's sound? Good morning also to the Facebook family. I need to get the link for the Facebook family, then send it also to out there. Okay, so guys, some people are saying my sound is very clear. Retabile, I'm only doing physical science today. That's what I had said on the groups as well. I'm only going to be doing physical science today. Yeah, pretty much. So I sent the handout to the group, but I'll also share the screen. The start of our lesson is 9:03. We'll end it in exactly 2 hours time. All right. To begin with, if you're using the book here, right, you go to page 30 if you're using the book, right? And then if you're using the handout, which I'm going to share right now on the screen, you are going to go to page 17. So let me share the screen on the handout now, the handout on the screen, and we're going to do page 17 very quickly. I'm going to start with that question. I intend on doing as many questions as possible. Again, people, if you don't understand something, raise your hand. Let me know if you guys can see the screen here. Can you? Right, just give me a shout if you can see the screen. I'll be happy about that, so that at least I can be able to know. Give me a shout if you can see the screen. Let me try and reshare this again. So that, okay, fine. Thank you. People can see the screen. I'm going to reshare it. There it is, right there. Let's begin our lesson. And we are doing page 30 if you're using the book, which is 2011 November, or if you're using the handout, which I'm sharing on the screen right now, again, is page 17. We start. A hot air balloon is moving vertically upwards at a constant speed. A camera is accidentally dropped from the balloon at a height of 92.4 meters, as shown in the diagram below. The camera strikes the ground after 6 seconds. Ignore the effects of friction. So here's my situation. So you've got a hot air balloon that is moving upwards. And when it's moving upwards, a camera is accidentally dropped. That's what the question tells us. When it's moving upwards, a camera is accidentally dropped. And then it's dropped from a height of 92.4 meters, as shown in the diagram below. And we're told that the camera strikes the ground after 6 seconds, and it says ignore the effects of friction. I'm trying to add people in here, so it's a bit of a mess. So allow me to administration issues, please. Let me try and add people. People are just coming in over and over again, but it's fine. Okay, so here's my situation. We'll start off with 3.1. At the instant the camera is dropped, it moves upwards. And the question says, give a reason for this observation. Okay, let's learn. Right. I want you guys to understand this. When an object moves upwards, when the hot air balloon was moving upwards and the camera dropped, the camera does not immediately go downwards. It doesn't. This is in respect to Newton's first law. The camera does not immediately go downwards when it's dropped. Rather, it goes upwards a bit and then it comes down. So this is a situation that happens. So the camera is dropped from 92.4 meters up there, then it goes slightly up, then comes down eventually. This is Newton's first law, which suggests to us that an object will continue in a state of motion unless acted upon by an external force. So here the question says, at the instant the camera is dropped, it moves upwards. Give a reason for this observation. This is an application of Newton's first law. So you can write that. Newton's first law is the reason why the object goes up a bit, then comes down. And that's a very important thing. The object was already in motion. You see, it was the balloon and the camera inside the balloon, and they were going up, both of them. So when you drop it, the object still continues, but for a short time, in its trajectory of going up, then eventually it comes down. So it's very important to understand that particular situation. So 3.1, please write it down, guys, in your books. So remember to write the title of the question. It's 2011 November. Paper 1 is question 3. And please write the title of the question as well. So 3.1, Newton's first law is the reason why the camera goes up first. One of my questions today I'm going to do is something similar, right? So keep that in mind. 3.2, calculate the speed VI, initial velocity, at which the balloon is rising when the camera is dropped. Calculate the speed VI, at which the balloon is rising when the camera is dropped. Okay, your choice of equations in this topic depends on the information given. So you're looking for the initial velocity of the camera when it is dropped. So let's clear the confusion. Now, normally when you hear a question saying a camera was dropped, the usual assumption is that its initial velocity is 0, dropped, fine. But in this case, the camera and the balloon were already in motion, so they had velocity already. So listen to the question. When you drop it, it is not initial velocity of the camera 0. No, it was already in motion. And what you're looking for is its velocity upon it being dropped from that particular balloon. And remember, when you drop it, it goes up a bit, then comes down. So you're looking for the velocity when you drop it. Let's get down to business. Check this out. Okay. Now, if I was to write or draw a diagram, this is what happened. So the camera went up slightly, then went down to this particular place to the ground. So when it went down, it covered a total of 92.4 meters. Let's clarify that. Now, the displacement from this start position where it was dropped to where it comes to, so it goes up and comes back to the same level, that particular displacement from there. The total displacement going up and coming down to the same level, that total displacement is equal to 0, suggesting to me that the camera went down a total of 92.4 meters. That's what happened. So let's get down to understanding this. Your choice of the equation again is influenced by the information given. So let me see what I have. All right, I'm looking for the initial velocity. That's what I'm looking for. So I'm looking for VI. I don't know VI. I do have G. It's a projectile. Let me say up is positive. That's what I usually say, but it's okay. You can only say down is positive, up to you. Up is positive, G becomes negative 9.8 meters per second squared. Then what else do I have? I've got the displacement, how far the object went. It went down 92.4, negative 92.4 meters per second. Very important. Further on, we notice that it took a total of 6 seconds. The question said it took 6 seconds to go down and cover that whole 92.4 meters. And then now the question is asking, what is the initial velocity? Your choice of the equation is influenced by the information given. And here I am. This is my equation I'm going to use. So delta y, negative 92.4. Initial velocity, I am clueless. How long did it take? 6 seconds. Plus a half. G is negative 9.8 since up is positive. Get this. I need to G, X, the acceleration due to gravity, X downwards. So therefore, the time there is 6 seconds. Somebody lifted up their hand, Zanele, and I'm going to unmute you. Zanele, give me a second. Let me unmute you. I need to hear what you have a question with. All right. Zanele, I'm unmuting you. Go ahead.
Good morning, sir.
Hi, morning.
Morning. I wanted to ask about when you wrote delta y equals negative 92.4 meters. You said per second.
Oh, yes, that's 92.4 meters. Supposed to be 92.4 meters. Sorry about that. Okay, it's just meters, not. Okay, I put the units for velocity, but it's just meters. Sorry about that. All right. Thank you, Zanele. Let's get down to business. We're looking for VI. So the rest is mathematics. Now, for today's lesson, I don't want to deal with the maths of it. You guys can calculate all by yourself. I want to make sure that I finish this up quickly and then make sure that I get the answer. So the VI, the initial velocity for this particular situation, two people raise their hands. Let me just deal with them there. Go ahead. It's Emmeline, I think. Let me just deal with you there, Emmeline. There.
Good morning, sir. I
Morning,
wanted to ask, why didn't we use the 10 meters?
Why didn't I use the 10 meters?
Yes, because it's being dropped. The camera is being dropped.
Okay, if you notice the 10 meters all has to do with the distance that there's a guy that looks like he's running, that's just 10 meters. But the camera is dropped from a height of 92.4. That 10 meters is a horizontal distance. And it looks like someone is coming through. Actually, it's coming in on question number 3.4. That's where it's coming in.
Okay,
right?
thank you,
so
sir.
you'll see that coming through on question number 3.4. Thank you so much for that one. Let's keep going, people. I'm going back to my screen there. All right. So on the screen, this is what I had written so that everyone can understand. I was saying to you, the delta y is equal to VI delta t plus half g delta t squared. So then my initial is my initial velocity, I don't know it, but I know my time, which happens to be 6 seconds. So let me write down the information properly here. So VI, I am clueless, but I know the time is 6 seconds plus a half g, the one which is negative 0.98, and the time taken 6 squared delta y negative 92.4. You do your math properly. VI is 14 meters per second, which for me is a measurement for velocity, and that's the initial velocity of the camera when it is dropped. Please write this one down, and we'll go to our next one very quickly. That's the initial velocity of the camera when it is dropped. I'm gonna give you guys maybe 5 seconds to finish this up. Initial velocity of the camera when it is dropped, okay? All right, beautiful. Let's keep going on that one. Let's work. All right, I'm gonna share the screen again and read the next question. Okay, now in the next question, what are we being asked in the next question? Right, we are asked to say, draw a sketch graph of velocity versus time for the entire motion of the camera. Indicate the following on the graph: the initial velocity, indicate the time at which it reaches the ground. Please be cognizant of this. You have 3 graphs that you must know: the velocity time graph, the acceleration time graph, and the position time graph. When it comes to the one that we're dealing with, the velocity time graph, it's quite interesting. I prefer that you write for me the velocity story. What did you see in terms of velocity? You're supposed to draw the entire motion of the camera. In other words, from the time that is dropped up until it hits the ground. You're supposed to draw that on the velocity time graph. Sharp. Let's go further. Let me draw the graph for you here so that you can see what's going on. So here's the point. In the velocity time graph, you will draw something like this. Okay, that's what you have. Velocity time graph. You must write time on the x-axis in seconds. You must write velocity on the y-axis measured in meters per second. So what is my velocity story? When the camera was dropped, it went up. It went up. with a velocity of 14 meters, and it's a positive one because I'm saying up is positive. Fine. It goes up and then it will stop. Stop is English. In physics, we say that its velocity is 0. Then it comes down all the way to the ground, and I don't know the velocity upon hitting the ground, and I can't assume it. It's not 0, that's obvious. I cannot assume it's 0 because it's not. Just because an object hit the ground does not mean that its velocity is 0. Not true. Fine. Now notice that at this level, when the object passes the same level that it came from, that it was dropped from, its velocity will be 14, just that it will be negative 14. This is a very important principle. If an object goes up, right, and comes to the same level, the velocity upon going up and the velocity of coming down at the same level, these two velocities will be the same. So at the instant the object passes through the point where it was dropped from, you will notice that the velocity will be 14, just that it's negative 14. Okay, I'm going to draw my graph right now. So I'll start off here at a positive 14, right? Where do I go to? So I'm going to tick this positive 14, done and dusted. Where do I go to? I go to 0. So my camera, there you are, I go to 0. From 0, where do I go to? Obviously, I'll pass through negative 14. There's my negative 14 there. Then I go to a velocity that I don't know. I just don't know this velocity. But one thing for sure is I know that the entire journey took me 6 seconds, right? Let me write my 6 just underneath there to make it a bit clear. And that's your velocity time graph. 6 seconds there, the time taken by the object to move from where it was, go up until it reaches the ground, and that's it. So write this down, people. Beautiful. Write this down. Okay, that's your velocity time graph there. Your velocity time graph. All right, let me go to the next one, 3.4. I think that's what Emily was asking me. 3.4. Let's read about this jogger. Someone is running on the horizontal surface. Let's go. If a jogger 10 meters away from point P, as shown in the diagram, and running at a constant speed of 2 meters per second, sees the camera at the instant it starts falling from the balloon, will he be able to catch the camera before it strikes the ground? Use a calculation to show how you arrived at the answer. Okay, let's clarify. Now, it takes the jogger, the jogger is running and he's running 10 meters away from where the camera will drop at. Fine. He's running at a speed of 2 meters per second. That's okay. Now he drops this particular, there's a camera that is dropped and goes to the ground. Logic would have it this way. If the jogger is able to catch the camera, then he must get to the point where the camera drops before 6 seconds. It looks like to me that the camera must take 6 seconds to go down to the ground. If the jogger must reach a place whereby he catches that particular camera, he must get there before 6 seconds, or at least at exactly 6 seconds, right? But before would be the most appropriate. So we need to calculate how long the jogger who is going to travel a distance of 10 meters at 2 meters per second, how long does it take for the jogger to get to point P? That's what we need to get. How long does it take for the jogger? Let me just show you from the diagram. It becomes a bit easier when you deal with the diagram there. Okay, follow my lead. Look at this. I've just shared the screen right now. So this is our concern. We are concerned about how long it takes for the jogger to get to this point. How long? Because that's the point where the camera will fall, right? So he's running at 2 meters per second. There is my information. He is 10 meters away. How long? So what am I given? I'm given distance. What am I given? I'm given velocity. What am I looking for? I'm looking for time. Since it's a horizontal application, horizontal, then I can use delta x. I don't know if you guys have seen this before. Delta x is equal to the velocity or the speed multiplied by the time. Delta x, the displacement on an x-axis, is equal to velocity multiplied by time. So how far is it going? 10 meters. How fast is it going? 2 meters per second. How long will it take? He will get there at 5 seconds. In other words, he gets to this particular place, point P, at 5 seconds. And therefore, we can conclude that he will catch that particular camera before it strikes the ground. So this is as simple as it gets. That's how you get the 5 marks. So the answer is yes, he will catch it, right? He will catch it before it strikes the ground. He will catch it before it strikes the ground. So all I needed was to find the time taken by the jogger to get to point P. From that perspective, then I can be able to calculate for myself how far or how long he takes. And then from there on, I can be able to tell whether he's going to be able to pick up the camera or not. All right. Thank you so much. That's your answer for that one. So that's our first question, family. That is 3.4. Please copy this down. Then we go to our next one very quickly. Again, if there are any questions whatsoever, kindly let me know. We have a lot of work to cover. I've got about 6 or 7 questions that I've pegged to do. Hopefully, I'll be able to do all of them, starting off with the easy ones, something that you guys can relate to. Then from there, I'm getting to the most complicated ones and very challenging as well. All right, beautiful. Let's go to our next page. Rather, we're going to our next question. If you're using the book again, I'm taking this out here. If you're using the book, we are on page 31. If you're using the book, 2006 higher grade, if you're using the book. But if you are using the handout, which I'll share right now, is page 18. If you're using the handout, it's page 18. Okay, Lebogang, you have a question. Go ahead.
Hello, sir, can you hear me?
Yeah.
So you're saying for 3.4, we use that equation if we dealing with the horizontal displacement.
Yeah, you do that. Use that equation if you're doing it. In fact, let me just clarify. You can actually use the equations of motion even on a horizontal scale. The equations of motion. The only difference is that on a horizontal scale, your acceleration, when you use that equation, your acceleration is no longer g. It's no longer 9,8. It's just the acceleration of the object. So you can use those equations of motion on a horizontal scale. But please take note that on a horizontal scale, we are not talking about projectiles. Projectiles are vertical, up-down movement. But that particular formula or those equations of motion can be used on horizontal scales. But take note, your G will not be 9,8 as it were. Talk to me. I got Gladys coming through. Right, I'm going to unmute you, Gladys. All right, thank you so much, Level. That's fine. Gladys, go ahead.
All right, good morning, sir. I think my question was related to the previous student because I also used the equation of motion, but I made my gravity 0. And then my time was 5 seconds. So I also, in that question, 3.4, I used that and my gravity was 0. And then the time I got was 5 seconds. And my conclusion was the runner would reach the time. So I wasn't quite sure if that was.
Right, this is my suggestion. This formula that I just gave you is the formula that we've always known. The one about distance being equal to speed times time. That's always the general formula about distance being speed times time. So in that instant, please just notice that I prefer that you use delta x equal to v multiplied by t. While I hear the option of saying I use an acceleration of 0, fine. But I prefer that you use delta x is equal to v multiplied by time. That's always easier from there on. Zanele, thank you so much, Gladys, for that one. Zanele still have a hand up. I'm not so sure if you want to say something or it's from the previous one.
No, sir, it's from the previous one.
Okay, sharp. Let me unmute Clara. She wants to say something. Clara, want to say something? I'm going to unmute you now. Go ahead. Clara, I can hear you. Go ahead. I should be able to hear you. Okay, we're not winning with her. Clara, then we can pull through. Okay, make sure you come through. Page 31. Yes, yes, you're here. Go ahead.
So I hope you're good.
I'm well.
So I joined in a little bit late. So on 3.1, I really don't understand how the camera moves upwards the instant it is dropped.
Okay, good one. I'm going to do a question like this. It's also on the book and also on the handout as well. The point is this. Let's not confuse the word dropped with the question itself. The question is starts off by letting us know that the object is moving up. The camera and the balloon, both of them are going up. That's it. They hit a speed. When you drop that particular camera, it does not go down immediately. No, it's against the laws of physics. It doesn't. Because the camera was already in motion, Newton's first law. The camera was already in motion, Newton's first law. So it goes up, then immediately comes down. So it does not necessarily straight up go down. Newton's first law says that an object will continue in a state of motion unless acted upon by an external force. An object continues in a state of motion unless acted upon by an external force, right? So it continued at 14 meters per second upwards. Then it noticed that it was outside the movement of the balloon. Then that's when gravity acted upon it and it went down from there on. So that's why it's like that. I'm going to do a similar question to this one. The one that I'm going to do next is very interesting in line with that concept that you just asked me right now, Club. Allow me to move on, people, as fast as possible. You're saying? You can go ahead, please. Go ahead. Yes. Okay.
Thank you.
I think she's gone.
Thank you, sir. Thank you. I understood. Thank you, sir.
All right. 2006 November higher grade, page 18 of the handout. I'm highlighting it here. It's on the handout there. And then on the book, it's page 31. Helen on a skateboard starts from rest without pushing herself forward. Now, that's a very interesting thing. She starts from rest, but does not push herself forward and moves along a track that is not horizontal for her entire motion. During her entire motion, she keeps both her feet on the ground. The graph below is a representation. Okay, let me just mute everyone. Okay. Now, the graph below is a representation of how her velocity changes with time. Ignore the effects of friction. So here's a graph. This graph is a graph of velocity and time for Helen. Now, let's discuss it. She starts from rest. So suggesting that when Helen started this whole thing of moving, her initial velocity was 0. And I think this point makes it clear. 0 right there. That's okay. Now notice from the graph that her velocity is increasing. The graph is going up. Now, I don't want you guys to think about the path that Helen is taking. Let's talk about her speed, her velocity. Not the path she's taking yet. We'll come to the path later on. Let's talk about the speed, her velocity. So velocity of Helen increases from here up to point P. So it looks like the moment Helen starts moving, her velocity increases. There, it's going up. The graph is going up. Then between P and Q, her velocity is decreasing. Okay, so between P and Q, her velocity is decreasing. Then between Q and R, her velocity is constant. The graph is straight like this. So between Q and R, her velocity is constant. The graph is straight like this. Okay, let's get down to business and understand what's going on. Now, in the velocity time graph, there are important things that we need to know. The first most important thing is this. The gradient of a velocity time graph is the acceleration. And I want you guys to write this down somewhere. The gradient of a velocity time graph is the acceleration, right? The gradient of a velocity time graph is the acceleration. Okay, that's fine. That's okay. Second point, I want us to learn about the velocity time graph. Second point, the area under a velocity time graph, keep writing, the area under a velocity time graph is the distance. The area under a velocity time graph is the distance. Okay, get that right? The area under a velocity time graph definitely is the distance. All right, so these are things that we must take home, must know about this, right? The area under a velocity time graph definitely is the distance right there. All right, let's go back to our question. Let's answer as many as we can. So here's my first one. Without doing any calculations, comment on the speed and acceleration in each of the following sections from start to P. Comment on the speed and acceleration from start to P. All right, let me just break it down for you. Follow my lead. Now, obviously, from start here up to point P, the speed is increasing. So my first thing is that the speed increases, right? The speed is increasing, as you can see. Then from start to P, acceleration. I said to you, the acceleration is always the gradient of a velocity time graph. And since it's a straight line, the gradient of a straight line does not change. So from start here to point P, the gradient is not changing. Why isn't the gradient changing? Because the graph is a straight line. So we can now comment on the acceleration. We will say to ourselves, yes, the speed is increasing constantly. That's true. There's an increase in the speed. It's a straight, smooth, straight line. Increase in the speed. But we will clarify and say to ourselves that the acceleration remains constant because we know that the acceleration is the gradient. And if the gradient of a straight line does not change, it also means the acceleration in this context does not change. So the two marks come this way. Speed increases, but acceleration remains constant, right? So write this one down. Those are the two things that are happening. Speed increases, but acceleration remains constant in that aspect. Follow my lead. I'm going on to my next one. Okay, I'm taking this out right there. Okay, beautiful. I'm seeing people are coming through, so I'm doing a lot of administrating issues here. So let me just finish that up. All right, so that's from start to P. Let's talk from P to Q. From P to Q, all right? That's all good and well. So from P to Q, we are clear. So from P to Q, there's a decrease in the speed. So I gotta write this down. So there's a decrease in the speed. It makes sense from P to Q, decrease in speed. But then what else do we notice about P to Q? Well, we notice that the acceleration remains constant. Again, it remains constant. Why is that so? Because I still, from P to Q, it's a straight line. And because it's a velocity time graph, the gradient of this straight line, this velocity time graph, is the acceleration. Therefore, again, from P to Q, the acceleration remains constant. Right, remains constant right there. All right, beautiful. That becomes your answer. All right, let's go further on this one. Acceleration remains constant and the speed is decreasing. Okay, I'm ready for my next one. Let's keep going on that one. Are you guys still okay? If you're still okay, then we're moving on. Let's keep learning on this particular platform. Here's my next question. It says calculate the magnitude of hair acceleration between points P and Q. The magnitude of hair acceleration between points P and Q. Let's agree. Between points P and Q, you need to find the gradient. Once you get the gradient, then you can be able to find your particular acceleration. P and Q are points on a graph. Now we speak a bit of some maths now. P and Q are points. So we just get the coordinates of P, we get the coordinates of Q, then from there on, we can find the gradient between P and Q. All right, so you guys can try and do it there. I'm gonna start on my part here. Let me get the coordinates of P first of all. All right, Jay Ramara, you raised your hand and I want to recognize you. There you go. Go ahead.
Yes, sir. It's about the good morning, sir.
Morning, hi.
Fine. How are you, sir?
Great,
It's
man.
about the previous question.
Yeah.
Sir, in which case would the acceleration, well, not remain constant on a graph? How would the graph look like? Yeah.
Okay, if the graph was like a parabola, the shape of the graph was a parabola, then yes,
Okay.
maybe I would understand. If the velocity time graph was a parabola, then I'll tell you that no, but it's not constant. Or it was shaped like a cubic, something like that, like a cubic.
Okay.
Any graph that is not straight, the acceleration is not constant.
Oh,
Right? Any graph
sir.
that's not straight. If it's straight, it's constant, right? Because
Yes, sir.
we know that for a straight line, the gradient is just going to be the same. You do
Same.
this in math when you do analytical geometry. To notice that the gradient for a straight line everywhere is always the same. So that's
Yes,
how
sir.
it is right there, Jay Amara.
That makes sense, sir. Thank you, sir.
All right, you're welcome. Let's keep going. Point P. I need the coordinates for P. Let me do and work out. Let me go there. That's like 1, then there's a 2 there. And then here, I think P, the x coordinate of P for me is 1,8. 1,8, the x coordinate for P, right? Let me check the y coordinate very quickly. Let me see what's happening there. So I've got 6 and 8 right there. So the units between them is 2. All right, that's fine. So the middle will be
8.
7, right? 7 right there. So I'm going to have it as 6,2, 4, 6, 8, 7. And I think that's 7,2. So for P, the y coordinate is 7,2. You can just unmute yourself, Ramara. It's okay. You can just mute yourself. It's okay. So guys, when you ask questions, don't forget to mute yourself. Let me just mute you there. That's fine. Right. So that's P. That's P. 1,8 for the X, 7,2 for the Y. Let me deal with Q. Right. Let me go to Q. That's 6 right there. You guys can check it out yourself as well later. Definitely that's 6,8 for the X-axis, 6,8. And then for the Y, right there, let me count. I've got 1, 2, 3, 4, 5. That's a 1 in the middle there. That's 1. So I can find the gradient of PQ. I can. And from math, gradient is Y2 minus Y1 over X2 minus X1. Right, let's go. Y2, 7,2 minus 1 over 1,8 minus 6,8. Okay, guys, I don't want us to waste much time with the calculations. I have the answers here. So my answer here becomes negative 1,24 meters per second. It makes sense why the gradient is negative, because there's a decrease right there. So it's a decrease in straight line. There you are. So the gradient is negative. And we say to ourselves, a gradient of PQ, we know it as the acceleration. So it's supposed to be meters per second squared. So the acceleration becomes negative 1,24 meters per second squared. Just like what you're looking at, and that becomes your answer for that one there. Please write that one down. That's fine. I've got the answers there so that I don't have to waste time on anything. All right, write that one down. Thank you so much. If there's any question, anything that's confusing, whatever the case could be, please, let's pull through, right? Okay, If you guys have a question, you just lift up your hand. I'll definitely attend to you, and that's fine. So let me take this out. A is called -1,24 meters per second squared. So it's important again that you notice that the gradient of the acceleration time graph is always your acceleration. Let's go to 4.3. 4.3. Compare the accelerations of the two sections up to point Q without doing any further calculations. That's 4.3. Compare the accelerations of the two sections up to point Q without doing any further calculations. Okay, now here's the point. So from start to P, right? Let me use a different color pen. Let me use red. From start to P, from O to P, the acceleration is positive. That's very true. There's an increase in the velocity, the acceleration is positive. Let me give you the implications. When there's an increase in the velocity, it means the acceleration is positive, but in essence, it means that the direction of the velocity and the direction of the acceleration are the same. Whenever acceleration is positive, like in this context, it suggests to me that the direction of velocity and acceleration are pretty much the same. From P to Q, you notice that our acceleration is negative. That means to me that there is a deceleration, negative deceleration, negative acceleration, deceleration. What is the implication? The direction of the velocity and the direction of the acceleration are opposite. In other words, Helen between PQ is slowing down. Her velocity is decreasing. Her direction of velocity and her direction of acceleration are different. So from start to P, there's an increase in velocity, positive acceleration. From P to Q, there's a decrease in the velocity, that's negative acceleration. So if you were to answer 4.3, right? So you're saying to ourselves 4.3, write the following. So I'll just read it as I have it here, 4.3. I would say to myself, the acceleration of OP, write down, the acceleration of OP, right, is in the same direction as the motion of Helen, right? The acceleration from O to P is in the same direction as the motion of Helen, as fine by me, as the motion of Helen, right? Then, full stop, then the acceleration from P to Q, then from P to Q is in the opposite direction to her motion. From P to Q, it's in the opposite direction to her motion or movement. So I need this cleared up again, last time. If the acceleration is positive, then it means that the direction of velocity, the direction of motion as well, and the direction of acceleration itself, they are the same. If the acceleration is negative, then you're opposing the displacement in that instance. And because you're opposing the displacement in that instance right there, it means then your direction of velocity and direction of acceleration, they will oppose each other. You are decelerating. You're preparing to stop, and that's a very important thing. Sharp. Let's keep going. I'm on 4.4, and it's a good 4 marks. Compare the shape of the track for the two sections up to point Q. Compare the shape of the track for the two sections up to point Q. All right, let's discuss. Now we're talking about the track that Helen is on. Now, if you go to the initial part of the question, and I want to highlight this, it says she starts from rest without pushing herself forward and moves along a track that is not horizontal for her entire motion. Okay, let me put this way. Okay, so the track that Helen is on is not horizontal. No. And when she starts, she doesn't push herself forward. No, she just starts to move. And remember, she's on a skateboard. And the question is saying, describe the track that she is on from the time she starts up until point Q. Let's do logic. If someone is on a non-horizontal track and that person does not push herself forward, and when she starts moving, she moves and starts to increase in terms of her speed. Because from the time she starts moving, Helen, at point O up to point P, her speed is increasing. Her speed is increasing. Sharp. So she's moving. Her speed is increasing. Then from P to Q, her speed happens to be decreasing. So what kind of track is she on? Do logic with me. If I want to start, and when I start, I don't push myself forward, then my track must be downhill. I must be going downhill. That explains why I'm here, and when I'm moving from there, I just go down, and I'm increasing in terms of velocity, by the way, and when I'm going down, I increase in terms of velocity. Then I move uphill. Then as I'm moving uphill, I'm decreasing in terms of velocity. So it looks like there's a downhill to head track and an uphill to head track. That's the only way you can explain starting from rest, moving without pushing yourself forward. So Helen's track is this one for a skateboarder. Downhill first, then she goes uphill. The word downhill motion, you're increasing in terms of velocity. The word downhill motion, your acceleration is positive. The word downhill motion, it means that your direction of acceleration and direction of emotion is the same. The word downhill. And when you're going uphill, your velocity is decreasing. That's true. Your acceleration is negative. That's true. You are decelerating. That's true. It means that your direction of motion and direction of acceleration, they are opposite, uphill. So you've got a situation of uphill and also downhill. And let me write down the answer now. It's no answer in our 4 questions, our 4 marks. Says compare the shape of the track, the 2 sections up to point Q. Write the following. From O to P is downhill. From O to P is downhill. Okay. The slope means gradient, by the way. The slope is constant. Okay. That's from O to P. From O to P, we're saying it's downhill. The slope is constant. Let's keep going. I need to give you the other one. Right, guys? Okay, people are asking me to record. That's okay. Already it's live on Facebook, so I can always download it from Facebook, and I will put it on the YouTube channel as well. So don't worry. It's being recorded by Facebook right now as we speak. So it's fine. Right, so we're going further. I'm saying to you from O to P is downhill. That's true. And then the slope means gradient is constant. We go. Then we say from P to Q, it's uphill, right? From P to Q, it's uphill. Uphill, the slope is constant as well. Slope is constant, right? From P to Q is uphill. The slope is constant. But let me add further information. Listen to me. Let me just write this here to be clear. So this is what you have. This is the track people, track there. Right, I'm just using this as an example. Because the acceleration is positive here, and here it's negative, then it means OP is steeper. That means you need to write this down. OP is steeper, right, than PQ. Steeper means that it's got a greater gradient than OPQ. So if you were to calculate the gradient of OP, it will be bigger in terms of magnitude than the one for PQ. Makes a whole lot of sense for me. So OP is steeper than PQ. That's probably the last point that you put there. So acknowledge that there's downhill, there's uphill. Acknowledge also as well the steepness of the path, that OP is steeper because already OP, you are going downhill, you are increasing in terms of your speed, therefore your acceleration is positive, therefore you are steeper than OPQ as it were. All right, I'm taking this out and we'll move on to our next one. Right, 4.5, we're going to put 4.5 quickly. 4.5, that was 4.4. 4.5 says calculate by using the graph and not any equation of motion, the distance she skates up to point P. Okay, let me see this. Calculate by using the graph and not any equations of motion, the distance she skates up to point P. I remember when I began this question, I gave you two very important things about the velocity time graph. The second one was the area of a velocity time graph is its distance. The first one was the gradient is its acceleration. So now they're asking us the distance that Helen travels from the time that she starts at 0 here up to point P. So the area of this whole thing from start to P would give me my particular distance. Now, obviously, I need to shape it up nicely, and definitely it becomes a triangle. And when I remember triangles in grade 8 or grade 7, I was told that the area of a triangle is always going to be half base times the perpendicular height. So let me get down to business. So the distance definitely is the area under this graph, half the base, that's from start up to this point where there's P, which we found already, if you remember, is actually 1,8. Then the perpendicular height is from here up to point P, which we found already as 7,2. And then my answer becomes a simple 6,48 meters. I must use what I know, the area of the velocity and time graph is always my distance. So 6,48 meters, and that's my answer right there. Okay, I want to go into another interesting question, something way more interesting than this, so at least we can be clarified and guaranteed of what we need to know. Okay, I'm ready, and I'm taking this out. 6.48, there you are, it's gone. Sharp. All right, beautiful. To take this out, and we take it up further. We're going to our next question, and that's 4.6. What is the resultant force on Helen between points Q and R? Explain why the resultant force has this value, and it's 3 marks. Okay, let's go between Q and R. What is the resultant force acting on Helen between point Q and R? Right. Now, if I look at Q and R, I see something very interesting between Q and R, right? Okay, Q and R. Now, if you notice Q and R, the velocity does not change. I've just spoken English there. The velocity does not change. Let me speak physics. Delta V, change in velocity, is 0 meters per second. Between Q and R, the graph is horizontal. That's velocity not changing. So the velocity of Q and the velocity of R is the same. Fine. Delta change in V is 0. But what's the implication? When there is no change in velocity, it means the acceleration is also 0. Now, this is super important. So the velocity is constant. Constant means that the change in velocity is 0. Guys, I did not say the velocity is 0. No, I said that the change in the velocity is 0, suggesting that the velocity at Q and the velocity at R are the same. There is no change in the velocity. So what's the implication of having no change in velocity? The implication is that the acceleration will become 0. It makes sense. If the graph is horizontal, let's speak math. If the graph is horizontal, the gradient of that graph is 0. So in this case, because velocity is not changing, then acceleration automatically becomes 0. But why am I even concerning myself about this? It's because I'm being asked about force. Force, net force, is the mass of Helen multiplied by her acceleration. Since now we know that the acceleration is 0. Automatically, the net force also becomes 0 newtons. This is specified more in the topic work, energy, and power. In work, energy, and power, you must know and hear this. If a question says an object is moving at constant velocity means that the change in velocity is 0. When the change in velocity is 0, it means that the acceleration is 0. When the acceleration is 0, it means that the net force is also 0. This is super important. So your answer is actually what I just wrote here. All of it, like this. Change in velocity is 0. Acceleration is 0 meters per second. F net, which is ma, will become also 0 in that particular aspect. So basically speaking, that becomes your answer. All right, I'm ready for my next one. All right, beautiful. That's lovely. You guys have been great. And let's go. Charisma, you got a hand up. I want to do that. Go ahead.
Good morning, sir.
Morning, how you doing?
I'm good, sir. So I want to ask, why did you say that your velocity from Q and R is 0 instead of 1?
Right, good. Right, Charisma, I did not say the velocity from Q and R is 0. No, I said the change in the velocity from Q and R is 0. In other words, the velocity at Q is 1. I totally agree. The velocity at R is 1. I totally agree. The change is always final velocity 1 minus initial velocity 1, and the answer is 0. So let me say this again. I did not say the velocity is 0. What did I say? I said the change in the velocity is 0. Not the velocity per se, but its change. All right? Because when you talk about change, you're talking about two instances, Q and R, and that becomes 0 for what I'm looking at right there. Beautiful one there, Charisma. Let's keep going. Okay, family, I'm going to my next question, all right? If there's any other question, you let me know. Remember, we're live on Facebook as well. I'm unable to go to my Facebook account now because I'm teaching here to be able to check the questions. But if you have any, try to put them through. I should be able to make a plan later on and help you on this one. We're going to our next question. It's not in the book. It's not. If you do have the full printed handout, which I think was a lot of pages, then it's there. But if not, I'm going to share it on the screen. I sent this handout to you guys on WhatsApp. So you have it as a document, a PDF file, PDF document. Page 39, that's where I'm going. And I'm going to share the screen here, and I'm going to go to page 39, right? So it's not in the book. No. I have it here on this particular handout there. And I'm on 2016 Senior Certificate, paper 1, question 3. That's where I am. And I'm going to do this question with you, and then we take it up from there. Right, so far, so good. Any problems, you let me know. We're taking it up from there. Please write down the title of the question, write down the page number. Anyone who may need this handout who doesn't have it, I should be able to put my numbers on this chat platform. I'll also do the same on Facebook before we go. You can just contact me on Facebook as well, so that at least I can send you this document and you know that you have what you need. I read, ball A is projected vertically upwards from the ground near a tall building with a speed of 30 meters per second. Ignore the effects of air friction. All right, let me just show you how it looks like. So that's ball A projected from the ground, and it moves up 30 meters per second. Okay, that's fine. Our first question says, explain what is meant by a projectile. Please, guys, listen up. Your marks for definitions are 2 marks. Definitions are 2 marks, or you're going to get 0. 0 or 2. There's no, I know a bit of a definition. I know halfway through. No. You must know everything, right? Explain what is meant by a projectile. Write the following. This is the motion of an object. This is the motion of an object where the only force acting upon it, motion of an object, where the only force acting upon it is force due to gravity. Motion of an object where the only force acting upon it is force due to gravity. Right, so that's a projectile, right? You could similarly define free fall the same way, the way I put it across: motion of an object where the only force acting upon it is force due to gravity. We go to 3.2. Calculate the total time that ball A will be in the air. Now that's interesting. Total time that ball A will be in the air, right? All right, somebody says their screen is blurred. Okay, let me just go to my phone and check if it's blurred. Okay, mine looks fine. I don't know, guys. Maybe you can just zoom in a bit just to make it a bit clearer and all. Hopefully it's not to do with my network here or ESCOM anyway, right? Okay, let's just try. If I just zoom in a bit, maybe you should be able to see what's going on. Calculate the total time that ball A will be in the air. Let's go to the object. Ball A, look at it. Ball A is in the air from the time that it is thrown until it gets back to the ground. That's ball A. It definitely will be in the air, right? So don't assume that it goes up and then it's in the air there, then it's only in the air on one portion, the upward movement. No. The upward and downward movement, ball A is in the air. And the question is, calculate how long it's in the air. Just as a disclaimer, and I forgot to say this when I started off, the answers to these questions, there are many methods of using equations of motions to come up with the answers. So I will not deal with option 1, option 2. There are many. I'm just going to deal with just one option. You guys can check the other ones in the memo that I'll send as well. Okay, so how long was ball A in the air? Up is positive. Let's have that. Use what you have. So what are we looking for? We're looking for time. How long? Now, what do we have? Now, we've got the initial velocity of ball A. We have it there, 30 meters per second upwards. Now, ball A will come to the ground. They didn't tell me this, but the fact that they asked me that how long will it be in the air, then I can say to myself, no, ball A can only go up and come down. So that's the whole portion. The going up and the coming down suggests to me that ball A is in the air, and that's fine by me. Ball A is in the air, going up and coming down. Now, because it comes down to the ground, the same point, same level where it was projected from, then I must think to say, oh, you're coming back to the same level. Therefore, the velocity on hitting the ground will be the same as the velocity on leaving the ground. So when A left with 30 meters per second upwards and comes down and hits the ground with 30 as well. This is a very important principle. When an object is projected from a certain point and comes back to the same level, the velocity of going up and the velocity of coming down, these two velocities are the same. It's just that they're opposite in terms of direction. 30 meters up, initial velocity, and then final velocity, 30 meters down. Up is positive, positive 30, up, negative 30, down. So now I know my initial velocity is a positive 30 because I said up is positive. Now I know my final velocity when I hit the ground is a negative 30. I need how long? The choice of the equation depends on the information given. VF, for me, you're looking for time, is VI plus UA delta T. A is acceleration due to gravity. VF is definitely negative 30, and I'm okay with that. VI is a positive 30, and I'm okay with that. Plus acceleration due to gravity, it always X downwards, and when I said up is positive. So G, negative 9,8. I'm looking for how long. I'm not going to waste time trying to do the calculations there. I have the answers. I did this yesterday, 6,12 seconds. So that becomes your answer. The whole time A is in the air is a total of 6,12 seconds. Please write this down, guys, and let's keep moving on that one. Okay, so I'm good on that. Up is positive. There we go. All right, let's go to the next one. Let's see what the next one is telling me there. And I'm going to take this out. Right there, Zanele. You lifted up your hand and I want to unmute you. Go ahead. Go ahead, Zanele.
Hi, sir.
Hello.
I just wanted to ask by the highest point where the ball is projected upwards, the highest point, the velocity is 0, right?
Yes. You can also use that portion to calculate time, but don't forget to multiply it by 2 because it's the time going up, now you need the same time coming down.
Okay.
You can use that same equation that I did, and you're using only for one portion. But make sure that the velocity I find now is 0 right there.
Yes.
All right.
So
that
if
becomes
you
the
if you
answer.
use that the first
But-
portion, you take your answer and you multiply it by 2.
Exactly. That's what you do. I just did it once and that was it. Okay. Ah, beautiful. Thank you for that one. Mute yourselves and then so at least you know we can pull through nicely. All right, let's go, family. We're going to 3.22. The distance traveled by ball A during the last second of its fall. Aaron. The distance traveled by ball A during the last second of its fall. Right, let's discuss. Okay, do logic with me, do logic. So ball A goes up, down 6.12 seconds. Okay. We're looking for the distance traveled by ball A for the last second. We don't know how far it went, the last second, we just don't know. So here's what you can do logically speaking. The total time taken by ball A is 6.12 to travel that whole distance. Now, if I'm able to find the distance traveled in 6.12 seconds, and I'm able to find, listen, the distance traveled in 5.12 seconds. The total journey is 6.12, yeah. Right, fine. So let me do this. So the total journey, 6.12. Let me try and draw this. Right, there. 6.12, okay. Then if I'm able to find the total journey for 6.12 and I'm able to find the total journey for 5.12, then I can tell you that therefore the distance for 6.12 minus the distance for 5.12 gives me the distance in the last second. Right there. So the total distance traveled 6.12 seconds. 1 second, for the last second, 5.12. So how far did I travel for the whole journey? 6.12. Like 5.12, I get it. Then I subtract these two distances. Then I should be able to get the distance traveled in the last second. So my logic starts here. Follow my lead. Work with me. Here's where my logic starts. My logic starts from this particular perspective, right? It says to me the distance in the last second, right, will be the displacement traveled 6.12 seconds minus the displacement traveled 5.12. That's all. Once I get this thing done, I'm good to go. And look at the formula that I'm going to use. Delta Y is equal to VI delta T plus a half G delta T squared. That's what I'm going to use. Then I'm going to say to myself, okay, let me deal with the 6 seconds, 6.12 seconds first, right? In this case, this is what I have. I'll have VI, the initial velocity. I wrote this for me. It's going to be quite a long one, but fine. VI is 30. How long? 6.12, right? Plus a half, up is positive, negative 9.8. And then the time is 6.12 squared, right? Minus the one traveled by the 5.12 seconds situation. Okay, let me take this out and put it on the screen, on a whiteboard screen. It becomes easier, right? I can write fully. So I'm saying to you, the displacement in the last second is the displacement covered for the whole journey, 6.12, and the displacement covered for 5,12. And I'm doing my maths here, and I say delta y, the formula I'm going to use is VI delta t plus a half g, in this case, delta t squared. All right, I'm good to go. And then I'm saying to myself, okay, so let me get the last one. The last second, how far? Delta y, that's 30, then 6,12 up is positive, remember, plus O half g, negative 9,8, times 6,12 squared. They are minus the one traveled by 5,12 seconds, still 30, but this time it's 5,12 seconds plus a half g, negative 9,8, 5,12 squared there, and you get your answer. I need to move quickly. It's negative 25,076, which can be written as negative 25,08. The negative tells me that is going down. So it's just 25,08 meters downwards. That's how far the object traveled in the last second. Talk to me. Talk to me. Right, talk to me, family. Let's get down to business. I like this question. It's logic. Check for the whole journey. Check for 5,12. Because I mean 5,12 obviously is 1 second before 6,12. So then you can check then, oh, I traveled 6,12. Okay, this is the 6,12. Let me go to the 5,12. Oh, so then 5,12 is 1 second before 6,12. So let me check how far I went. So say the total 6,12 distance traveled minus 5,12, and you get your answer is 25,08. I want to move on to my next one. Quickly. Let's go further. Right. There's a second ball introduced in the team right now, ball B. Ball B is in the team. Right, I'm taking this out, family, and here it goes. 5 more seconds, and I take it out, and here it goes. All right. We're going to our next one. And I'm sharing the screen, and I'm going to read. 3.3, still on page 39. 2 seconds after ball A is projected upwards, ball B is projected vertically upwards from the roof of the same building. The roof of the building is 50 meters above the ground. Both balls A and B reach the ground at the same time. Refer to the diagram below and ignore the effects of air friction. All right, let's go to the diagram. So 2 seconds after ball A goes up, ball B follows. 2 seconds after. Okay? And then the question further on tells me that they reach the ground at the same time. Okay? So let me see. Ball A moved from the ground and reached the ground at 6,12 seconds. Ball B moves 2 seconds later, but reaches the ground at the same time like ball A, but 2 seconds behind ball A. Okay, I need to think now. What these guys, what are they talking about? So for ball A, how long did it take you, ball A, to reach the ground? 6,12 seconds. Good. Ball B, you moved upwards 2 seconds after ball A was projected. Yeah. And when up ball B, you're going to reach the ground at the same time like ball A. So it looks like to me, logically speaking, if ball A took 6,12 seconds, ball B to reach the ground at the same time like ball A took 4,12 seconds. No. Let's think. 6,12 by ball A, 2 seconds later, ball B Same time on the ground, then ball B must have gotten there in 4,12. Look at the logic. It takes ball B less time in comparison to ball A. Because ball B is already behind by 2 seconds. So ball B gets to the ground 4,12 seconds. The total time from the time it's projected upwards until the ground, 4,12 seconds. For ball A, it's 6,12 because ball B, remember, is behind by 2 seconds. He's thrown after ball A has already gone. It's like a relay, like a race. Somebody starts moving fast and travels 100 meters. Let me give you an example. It travels a good 100 meters of a, let me say it's school and you're running 100 meters, 6,12 seconds. When now you move 2 seconds before after him, then that means for you guys to get to the same point at the same time, you must travel 4,12 seconds. And it means, logically speaking, you're faster. It took him 6,12 seconds to get to 100 meters. You took 4,12. You took less seconds, but same distance. You're faster. Okay? Let's break it down. Let's go to our question now. Calculate the speed at which ball B was projected upwards from the roof. Let's break it down. Speed at which ball B was projected upwards from the roof. So I'm looking for the initial velocity of ball B. All right. I don't know what it is, but I can get down to business. All right. What do I have? Obviously, it's a projectile, so there's G up is positive. What am I looking for? I'm looking for initial velocity. Do I know how long it took to get to the ground? Yes, I do. It's 4,12 seconds. So now, how far did I go down? 50 meters. Look at this. You go up, I agree. Then you go down. And the total displacement is actually 50 meters. It's the height above the ground from where you were projected from there to the ground. So delta y for me would work VI delta t plus half G delta t squared. Guys, I always say up is positive, but you can do whatever you want. You can always say down is positive. That's okay. I prefer up as positive. That's fine. In the exam, please put a disclaimer, up is positive, and you put it across that way. Let's go. So delta y in this case is 50 meters. It's going down. So it's negative 50 for me. Is equal to initial velocity of B, which I don't know. The time taken 4,12. You see, that's what I was thinking about. 4,12. Half up is positive, negative 9,8 times 4,12 squared. I'm not going to waste time. I want us to do VI. VI is basically 8,05 meters per second. It's a positive number showing me that the initial velocity, because ball B went up first, then came down, is 8,05 meters per second. And that becomes the answer for ball B right there. Okay. Hoping that people understand this, and that's okay. Let's go to 3.4. I want to draw a graph. 3.4. 3.4. I want to draw a graph on 3.4. Okay, write down that one there. I want to create the drawing here. Hoping that we're learning vertical projectile motion. Okay, very beautiful topic. I'll see if I'm going to do another free lesson. I'm quite busy, and with ESCOM also messing us up, I don't know. We'll see. I'll update you guys. On some of the most difficult topics that you may have. I am though going to send a video probably now on my Instagram page and my my Facebook page as well. Instagram is Mr. X Math Science, right? You can find me there. I'm going to send a video for maths though. It's going to be about transformation graphs, transformation. I just need to do the handout first, and then maybe just do a 15-minute video and put it on my Instagram page. I'll send the link as well to the groups, and maybe I'll also put it on Facebook. That's fine. It's about transformations in terms of AMA functions and graphs. All right, I'm taking this out. There we go. Next question. The next question says to me, sketch the velocity time graph for the motion of the balls A and B on the same set of x's. Clearly label the graph for balls A and B respectively. All right, indicate the following on the graphs. time taken by both A and B to reach the ground, time taken by ball A to reach the maximum height. Okay, let me just draw it here while you guys are looking at it. I'm going to draw the velocity time graph, and they wanted to draw it on the same place, eh? Like same place for both A and B. Let me use different color pens. Let me use green for A. Okay, let me deal with A. So A went up at 30 meters per second. I agree. It's a positive 30 meters per second. That's for A. Obviously, it's going to get to this point A where it stops. That's its highest point. So it's going to get to a velocity of 0. That's okay. And then it's going to come down and hit the ground. And it's going to have a velocity of negative 30. So there's 30 there. And then here, there's negative 30 right there. And I noticed that the time taken by A, the wall time, is actually 6.12 seconds. So the time here will be 3.06. That's half of it, because we noticed that from there to there, it's 3.06. From there to there, 3.06. The total journey becomes 6.12. That's for A. So A, the green graph, let me put A there. Let me try B. Let me try B. Now B is interesting. B starts 2 seconds later. Let me use blue color for that one. So B, I can't start it here. I'm going to start it here 2 seconds later. And notice that the velocity of B, when it starts, we calculated it is 8.05. So let me just come here quickly and say 8.05. And then where are you starting B? 2 seconds later, it's like these are like dotted lines. Okay, I'm the worst person to draw anything in the world. Not good in drawing, forgive me. Let me try this. Okay, let me put 8.05 somewhere there. They are. And then for B, I'm gonna go all the way. Remember, you end up getting to the same point there, same logic like that one there. So that's just for graph B. Same time, you're gonna get there at the same time there. And then maybe just put dotted lines here, there. That's graph B. Straight line everywhere, time in seconds, and then here, velocity in meters per second. This becomes the graph of B and A on the same set of x's. B and A on the same set of x's. All right, we're good on that. B and A on the same set of x's. But in line with the questions that we're doing now, let me do something a bit more challenging than this, because I want questions to do right now. I want questions to do with 2 balls moving up, down, whatever. Let me do a question again on that. It's on the book this time. It's page 34, but it's also on the handout, and it's page 22 on the handout. Page 34 on the book page 34, but on the handout, it's page 22. I think we're done with this question here. I think we should be done here. I'm going to take this out very quickly. Just give you guys a couple of more seconds on that. All right, it's gone. Page 34, 2015 November. Page 34, 2015 November. Right? Okay, beautiful. Page 34, and then here it's on page 22. I'm just going to go to the screen very quickly and write page 22. There we are. I'm going to start reading. Let's go. Family, please write down the titles of these questions together with me, and then we take it up from there. Ball A is projected vertically upwards at a velocity of 16 meters per second. Okay, so A by me from the ground. So let me just look at the total full diagram, something like this. Ignore the effects of air resistance. Use the ground as 0 reference. When they say use the ground as 0 reference, they're just simply saying your ground becomes your x-axis when you draw your graphs. Okay, the ground is 0 reference. Calculate the time taken by ball A to return to the ground. This is interesting. There's ball A. So ball A, this question and the previous one, they are almost similar, but slightly different. So ball A goes from the ground up 16 meters and then comes down. And the question says, calculate how long it took for ball A to come down to the ground. In the previous question, it was phrased this way. It was, how long was the ball in the air? In this time, they're asking you, calculate the time taken by the ball to reach the ground, right? So it goes up and down. And because it comes back to the ground, again, the logic that I gave you in the previous one applies, okay? We know that the initial velocity is 16 meters, up is positive for me, up is positive, fine. And so it went up at 16 meters, it will come back to the ground, and because it's coming back to the ground, its velocity upon impact with the ground is 16 meters, just that it's a negative 16 meters, that's all, okay? I'm okay with that. Fine. What am I going to use? I'm looking for time. Same thing like the previous one, right? I want you guys to know. That's why for me, it's very important that you know this. Negative 16, there we are. Initial is a positive 16. Up is positive, negative 9,8. I'm looking for the time taken to come back to the ground, 3,27 seconds. That's your answer. Somebody could have said this, say, can I not find the time taken to move from here to the highest point? Yes, you can. And how do I know stuff? I know that the initial will be 16, the final at the highest point will be 0. I get the time taken here, but I'm not looking for the time from start to highest point, but rather until I get to the ground. Don't forget to multiply that number by 2. Don't forget that. So write down this answer, guys. So answer there, write this down, and that's your answer right there. Okay, I think I've moved a bit. There you are. Okay, sorry about that. Then I think they should be able to come here. Okay, there you are. And that's fine by me. And I'm going to take this out now. Let me take this out. There. Okay. Next one says what? Sketch a velocity time graph for ball A. Show the following on the graph. Initial velocity at A. Okay. Time taken to reach the highest point. Time taken to return to the ground. Okay, so I need those 3 things. So velocity time graph, that's okay by me. Right, so let me draw that one there. So let me do my logic. What's my story? I went up at 16 meters per second. So up is positive, 16 meters per second. So I'm going to put it here, 16. Then I must have gone up to my highest point, which was 0 and something like that. And then I went down to the ground. And when I hit the ground, I was at negative 16. And they want us to, it's a straight line, guys, don't worry, it's a straight line. And this one here is 3,27, right? That's it. That's what they wanted. Time in seconds, velocity in meters per second. So you can just quickly write this one down. There you are, just write that one down there for me. That'll be fine. Okay, we can quickly go to our next one. Right, I'm going to take this out now. I'm going to go to my next one there. I'm taking this out. There we go. Right, here's the next one. It's a very interesting one. Then I'm going to try and see if you guys can do maybe one question in Yana. We'll revise it together, and then we'll probably close our session because I can't do everything alone. You guys must also get involved as a family. English, we go. 1 second after ball A is projected upwards. 1 second after ball A is projected upwards. A second ball is thrown vertically downwards at a velocity of 9 meters per second from a balcony 30 meters above the ground. Refer to the diagram below. Okay, what's happening here? So ball A goes up, fine. 1 second later, ball B comes down. Ball B is thrown downwards. Guys, there's a difference between dropping something going downwards and throwing something. Dropping means initially 0, I agree. Dropping 0, throwing cannot. That's why they even gave you a velocity, a downward velocity, even on the diagram is there, is 9 meters per second. 6 marks is the question. Calculate how high above the ground ball A will be at the instant the two balls pass each other. Yeah. How high ball A will be from the ground at the instant the two balls pass each other. Sharp. Let me go to my whiteboard screen. It will make sense from there on. Okay? Somebody just sent a message. Ufuma says, say for the previous question, they asked for the time taken to reach the highest point of motion. And that's, I think the previous question was 3,2. Yeah, the highest point, oh, that one there. Then that must be half of it. Time taken to return to the ground. Okay, fine, I see what you're talking about. So in the graph there, and I skipped that. In the graph there, where there's 3,27, right? Half of it there, that's the time of it. So 3,27 there divided by 2, the time there should be 1,64. So maybe somewhere here, just put 1,64 in the previous one. Thank you for that one. The time taken to reach the highest point of the motion at 1,64. Right, I hadn't put that one there. Let's move on. All right, so I'm still on this one here. 1 second later, ball B goes down at 9 meters per second. And then we're looking for how far ball A would be when it passes through with ball B. All right, let me go to the screen, the whiteboard screen. Logic, people, let's work. Okay, here's my thought process. I don't know the time taken by ball A and ball B. I don't know the time taken by ball A to come down and meet with ball B. I just don't know. So I don't know how long it took for ball A to come down, and then for ball B to come down rather, and then for ball A to go up until they both meet. Because I need to find out how far ball A would be when they meet. So I just don't know how long it takes ball B to go down and ball A to go up and they meet together. I just don't know. So that's okay. I also don't know how far ball A has to go down, ball B rather has to go down to reach the same point with ball A. I just don't know. I just don't know much. Well, all I do know is their initial velocities. That's all I know. I know the initial velocity of A going up. I know the initial velocity of B coming down. I don't know how long it takes for them to meet at the same time. I don't know. I don't know how far they would have gone. Actually, that's what I'm supposed to answer in here, the how far part of it. So let me just think. Let me write stuff. I don't know, but let me write. Let me say to myself, okay, so the delta y, the displacement, I don't know it. I do know the initial velocity, the time, I don't know it, right? Plus half g delta t squared. Now, let me get the distance traveled by A, right? By A. Let me just get it. Up is positive. So I'm going to have 16 delta t, right? Plus a half g negative 9,8 and then delta t squared. Let me do some logic. 16 delta t minus 4,9 delta t squared. So that for me is the distance traveled by A, and the time taken, I don't know. I just don't know. Fine. Let me get the distance traveled by B. Same logic. Traveled by B. Let's try B this time. Okay. So for B, distance traveled by B, right? Look at the logic. B up is positive, so it's going down. It's going to be -9. But here's the key. 1 second after. 1 second. So if they meet, because they're going to meet at a certain point, if they meet at a certain point and it took t time to get to that point, listen, if they meet at a certain point and it took t time, t as in the letter t time to get to that point, then A and B will meet at that point at the same time. But for B is behind by 1 minute. In the previous, the other full question that we did, 2 seconds later, we knew 6,12 and we said -2. We got 4,12. This time, it's 1 second later and we don't know the time. But we do know it's 1 second later. We just don't know the time. Back then we said 6,12 -2. This time we'll say the time -1. Oh, okay. So I'm here. VI delta T for B is the time -1 plus a half G negative 9,8, the time -1. Ah, there you are. Let's do math. Let's do math. Okay, let's open up the brackets. Let's do some crazy math here. So if I open up the brackets nicely, I'll have negative 9 delta T, right, plus 9, right, minus 4,9. Half of negative 9,8 is 4,9. Then delta T squared, I do logic in maths. It's like delta T squared minus 2 delta T. I'm opening the brackets properly, plus 1. That's what I have. Open the brackets up nicely, negative 9 delta T plus 9, open up the brackets, minus 4,9 delta T squared, okay, and then also plus 9,8 delta T minus 4,9. Group the like terms together. Let's see if they make logic on my side. So when I group the like terms together, which ones? Let me use a red pen. This one goes with that one. I must get a positive 0,8 delta T. Who's next? This one is on its own, minus 4,9 delta T squared. These are the numbers, 9 and negative 4,9. I must get a positive 4,1. That's delta YB. So that for me is a distance traveled by delta YB. These guys must meet at the same time. They must meet at the same place, same time there. Then what? Check. Now, look at the diagram. So from where B is projected, B, and then from A, there, to logic. A goes up a certain distance, B goes down a certain distance, right? Where they meet, let me put M for meet. Where they meet, the distance traveled by B downwards plus the distance traveled by A upwards should be equal to 30. That is the height of the building. Definitely. Where they meet, the distance traveled by A upwards plus the distance traveled by B. And remember, downwards is negative because upward is positive. The B travels downwards, so it's going to be a negative YB. Their total distance must be equal to 30. Right there. That for me is the key for finding the answer to this question. Remembering that the distance traveled by A upwards and the one by B downwards, added together, they give me 30. So, but say, what is YA? Well, YA is 16 delta T minus 4,9 delta T squared. I found it there. There's YA there. And then plus minus YB. So plus, let's do this, do logic. Minus, what is YB? 0,8 delta T minus 4,9 delta T squared plus 4,1. All this is equal to 30. So the T, let me do math. Work with me. I can open up the brackets as quickly as possible. I don't want to waste time here. I want to make sure that this is clear. So look at what I'm going to do. The 16 delta T here, it goes with this number here, negative 0,8 delta T, because I'm opening up the brackets, negative 0,8 delta T. It will give me 15,2 delta T. Then there's obviously this number, negative 4,92 4,9 rather, delta t squared. Then there's a minus outside and a minus there. That's a plus right there. So it's negative 4,9 delta t squared plus. Okay, fine. Let me write it. Okay, let me write it. Yeah, so that I don't have to struggle with you guys. Okay, 16 delta t. Let's do it old school, like a good family. There are. Okay, I'm opening up the brackets. There's a plus there. Then that's minus 0,8 delta t plus 4,9 delta t squared minus 4,1 is equal to 30. So we do it nicely again, use a different color. Let's do logic. 16 delta t minus 4,9 delta t squared. There's a plus inside there. There's going to be negative 0,8 delta t plus 4,9 delta t squared minus 4,1 is equal to 30. Okay, let me just do it now. Like terms, this guy and that guy, 15,2 delta t. This guy and that guy, 0. Then I have got this guy taken to the other side. It becomes 30 plus 4,1, 34,1. So the time taken for them to meet right there is definitely going to be equal to 2,24 seconds. I'm not looking for time, Mina. That is not what I'm looking for. I'm not even any close looking for time. I'm looking for how high, how far A was for them to reach the same point. Then I'm done with my question. Check this out. Do logic with me. There you are. Do logic. So now that I know the time that they will meet, right? Then it means to me the distance that A has to be 16 delta t, which for me in this case becomes 2,24, and then minus, I'm here, minus 4,9 delta t squared, 2,24 squared, and the answer simple becomes 11,25 meters above the ground. That's when they meet. That's how far A would be when it has, that's how far A would have traveled to actually go down, to go up rather, and meet up with ball B. That becomes the answer. I'm waiting for questions. That's what I'm waiting for. Right, you can write this down, then you can ask me questions. So I can just, when I'm explaining, if there's a question, I can always go up, I can say, this is what I did, this is my logic, and stuff like that. There are many ways of doing this again, many different ways. This, I can guarantee you, is the easiest way. Talk to me, family. Talk to me. Lebohang, there you go. Got your hand. Talk to me.
So, from where you like derive the Martinez equations. So,
where I had YA and YB.
yes,
Okay,
so from where you do your equations.
Where I equated, okay, let me use a different color pen. All right, so are you saying from here, like here? Okay,
No, sir.
Okay, all right, so here was my logic, ne? A, B, 30 meters, that's the height, right, of the building. B is going down and A is going up. So the time that they meet, when they meet, right, A would have covered a certain distance and so would B. But because B is projected exactly from the top of the roof and is going down, and B is from the ground and is going up, then it means to me that the distance traveled by B going downwards and the distance traveled by A going upwards, these two distances are, no, they're not the same, but when you add them, they should give you 30. Because that's the 30. They're coming from, one is coming from the base and is going up, one is coming from the top and is coming down. And from base to top is 30 meters. So what B covers going down plus what A covers going up, total, both of them must give you 30. This is why I'm able then to say Y of A, the distance covered by A going up, plus the distance covered by B coming down. And remember, for my case, YB is negative because I'm going down. And I say down is negative because for me, up is always positive. That's why it's YA plus minus YB. Then from there on, I'm able to articulate myself and say, oh, okay, I do know YB. It just happens to be 1 second later. That's all. And I did the math here. And I add these two, and I get up to find the time taken to go up by A, right? I can also do the same for B. I can find the time taken by B to come down where they meet. Obviously, I need the distance traveled by A, so I know the time. The whole idea of equating those two numbers was to get the time. And once I get the time, I substitute it here, and I'm able to find how far it went.
Okay, sir.
Are you
Then
okay?
you're wrong when I write like delta t squared minus 1. Like I did not say delta t minus 1 all squared. I just said delta t squared minus 1.
Oh, okay. All right. No. It's t minus 1 squared, right? That's how it should be. All right. Thank you for that one, Lebo. That's beautiful. Okay. You guys okay? We're almost to the end of our lesson anyway. All right. Just write this down. Facebook family, are you guys okay? I'm going to check you out now. Yes, there's 16 of you watching. Okay, I can see you guys. What's happening, right? It's good. Let's keep going and moving on to the next one right there. I'm going to upload this meeting on I'm just going to download it now after we're done, and I'm going to upload it on the YouTube channel, and then I'll see other things that I can do as we're going along. Okay, I'm ready for my next one. I'm taking this out. Is there a next one? Nope, there's no next one. Now I'm going to give you a question to try. It's actually, I like this question. It's also on the book. It's an old question from 2005 higher grade rather. It's page 26, 2005 November. That's 26 of the book. Let me look for it from my notes here for the handout. For the handout, it's page 13, 26 of the book. For the handout, it's page 13. I actually like this question on that one. Okay. I'm taking this out. Let's do logic. So we are on page 13 of the handout, and on the book we are on page 26. So please write that one down. The 2005 November higher grade. 13 right there. Let's go. All right, let's do logic. A crane in East London Harbour lifts a crate mass 300 kilograms from the deck of a ship. It then moves the crate horizontally above the surface of the water and stops. The crate is now lifted vertically upwards at a constant speed. When the crate is 30 meters above the surface of the water, while it is moving upwards, see, now for me, this is the most important thing. While it is moving upwards, I need to mark that. So when the crate is 30 meters above the surface, right? Above the surface of the water, while it is moving upwards, the cable holding the crate snaps. The velocity time graph below represents the motion of the crate from the moment the cable snaps until it hits the water. Downward motion is taken as positive. Oh, okay, good one. This time they don't do what I do. Downward motion is taken as positive, and the effects of air resistance can be ignored. All right, so the 2005 November higher grade. Let me give a disclaimer very quickly. The education syllabus changes over and over again to meet the current needs of the industry. So in 2005, G, acceleration due to gravity, was 10. It was 10, exactly 10 meters. They rounded it off. For us, it's 9,8. Okay, so acceleration was 10 then, 9,8. We're going to use 9,8 for our questions today. Secondly, the equations of motion back then for the higher grade syllabus, when it came to how they were written, the final velocity was just given by the letter V. So V meant final velocity. The initial velocity was given by the letter U. That's in 2005. And the displacement was given by the letter S. So let me say that again. V, final velocity, U, initial, S, it is definitely the displacement. If you look at even books that are written now, there's still, some of them use this method, V being final, U being initial, and S being the displacement. But we now know it's VF, VI, and delta Y. So that's okay. So you're given the graph, and the graph contains these old units, right? There's my graph. There's my V, there's my U, and then there's the time. Okay? And that's fine by me. 3.1, what does the gradient of this velocity time graph represent? State also, without doing any calculation, the magnitude of the gradient. So let's do logic. When did we start speaking vertical projectile motion? We started speaking vertical projectile motion when the cable broke. The cable snapped. So the crate was moving upwards, okay, was moving, boom. The cable breaks, then it goes down. And that's okay. Right. Similar to my first question about the similar to my first question about the camera. The cable breaks while the crate is going up. So the crate does not immediately go down. No, even the graph actually shows you. The crate does not immediately go down. It goes up first, then down. Okay? So the crate was moving Newton's first law. The crate was already moving Newton's first law, right? And then the cable snapped, so the crate goes up slightly, then down. Question is, what does the gradient of this velocity time graph represent? My answer is acceleration. State also, without using any calculations, the magnitude of the gradient. Because we're dealing with the graph of a projectile, then yes, 3.1, my answer is acceleration. I agree. And the magnitude of that one is basically 9.8 meters per second. If we were still in 2005, we would have written 10. But because now we're in 2021, we're writing 9.8 meters per second. So 3.1 answer, acceleration, that's the gradient of velocity time graph. I showed you this in the graph in Helen. I did that. State also, without using any calculations, the magnitude of that gradient. So that's 9.8. Right, let's keep going. I'm ready. Right, let's keep going. I'm ready. Determine the speed, the constant speed u with which the crate was being lifted before the cable snapped. Right, let's do logic. So the one u, right? I don't know what u is. Definitely, I don't know. And then I know this point though. I don't know much about this. So where there's u, it's the y-intercept. The x-coordinate is 0. The y-coordinate is negative u. And where there's this point here, the x-coordinate is 0.2, and the y-coordinate is 0. I know something now. I know that because it's a straight line graph, it's a velocity time graph. From my first answer of 3.1, the gradient of this graph right here, even this point from here to there, the gradient is 9.8 rather, which is the acceleration. So then I have the point and I know the gradient. I know the gradient, it's definitely 9.8 right there. I know the gradient. And they say down is positive, remember? Down is positive, that makes it a positive 9.8. So then I can find my u. I can. How do I do it? Well, I would say y2, okay, let me use a different color pen. y2 minus y1, 0 minus u over x2, all right, minus x1, there you are. This gradient, all of it is equal to 9.8, and I'm just looking for u. So 0 plus u at the top is u. Then I'll cross multiply everything here by 0.2. It is 0.2 minus 0, 0.2. Cross multiply, u is just 1.96 meters per second. Obviously, it's a negative number when I think about the fact that, look at it, it goes up, then comes down. So it means that here it's going to be negative 1.96. I just gave you the magnitude of it, negative 1.96. Then obviously here it goes up the crate, then it will stop somewhere and eventually comes down, right? And we don't know the velocity when it comes down. That's the V, the final velocity on hitting the ground. We don't know, or the water rather. It's the water that we're talking about, surface of the water. So the answer is that 1.96 meters per second. Let's go. Okay, 3.3. So that's 3.2. Let's go to 3.3. We're about to finish our lesson. Let's just finish this question. Then we can quickly say goodbye to one another. You guys have been wonderful as well. I think you guys are amazing human beings, and I know you're gonna pass. Okay, we just need to work harder and push ourselves. Keep fighting the battle. It's not gonna get easy. Sometimes it will frustrate us. Sometimes we get angry at ourselves, but we are going to make it. We keep running, we keep pushing, we keep moving. We want to make sure that we get the best marks at the end of the day. We must work like people that want 80s and 90s in the final exam. So whenever you feel discouraged, remember the goal, boy. Remember the goal. Remember the goal. Where are we going? What, going to the 80s and to the 90s. All right, sure. Here we go, 3.2. 3.3 rather. Determine by using the graph, but not any equations of motion, the maximum height the crate reaches above the position where the cable snapped. Right, let's do logic. So what am I looking for? They said determine by using the graph, not equations of motion, by using the graph, the maximum height the crate reaches above the position where the cable snapped. Okay, let's do some logic. So for me, this is where the cable snapped. And when it snapped, the crate went up and came to the surface, which is the water. Now, as to what's going on here, this is the logic. So from this particular point, I know that my velocity is negative 1.6. Up is negative because down is positive. I need to keep reminding myself that. And I'm looking for, what am I looking for? The maximum height which the crate reaches above the position where it snapped. And so I'm looking for the maximum height. That's from just here to this point. And I must not use any equation. I must use the graph. So when do I get to maximum height, right? When the final velocity is 0. So if I look at my graph, the velocity is 0 right here. And I started off here. And I said in the question about Helen, that other 2006 higher grade, I said the height, the distance is the area of the graph. So the area of this graph, this portion, that's the height. And area, that's a triangle of triangle, is half the base, there you are, times the perpendicular height, there you are. So half the base. So the base is this part here, this part. We use a red color, this part here. That's the base, which for me is 0.2. The height is from there to there, and that for me is actually 1.96. Obviously, I'll put negative there, but still the same thing. I'll get the same answer in terms of magnitude. So I get an answer like negative 0.2 meters. So in other words, it's 0.2 meters upwards. Remember, up is negative because down is positive. So that's my area. That is my distance. You must keep remembering that the area of a velocity time graph is your distance traveled. So they want it for the maximum height, not for the total journey, just for the maximum height. And at the maximum height, my velocity is 0. So I started off here. So the area underneath this portion here, definitely gives me my distance, my height traveled. Area of triangle, half base times perpendicular height. Okay, 3.4 family. Let's go to 3.4. 3.4. Now, 3.4, there are about 2 or 3 ways of doing it. So remember, they are using 10, and so I'm going to use 9,8. So I'm going to use the method where if we use 9,8, we'll get the answer like them, right? But again, guys, it's just the fact that it changed. Pretty much, it was the answer. The physics is the same, right? Let me just take this out and go to the last question, which for me is 3.4. Without using the time of fall. All right, without using time, that the magnitude of the velocity v with which the crate strikes the water after the cable is snapped is 24,58. So show without using the time taken to fall that the crate the velocity at which the crate strikes the water is 24,58. So they don't want me to use time. If you want to go to your equations of motion, almost all of them have time, except I think equation number 2. Let me clarify. Let me just show you from here. Maybe you guys can see this from the notes. They are, yeah. Every one of the equations has time, except this one. This one here, equation number 2. Let me just annotate it from here. There we are. There. Except this one doesn't have time. Okay. So we are supposed to show that when the crate hits the water, it hits it at 24,58. All right, sharp, 24,58. Let's go back to the question itself, and then we clarify. 15. All right. Let me do the logic. So I'm going to use the second equation because that's the one that doesn't use time. Time of fall, it doesn't at all. So then I'm going to say to myself, V F squared is VI squared plus 2G delta Y. And I'm fine with that. Let me do it on a screen, a whiteboard. So here's the logic. I mean, I came all the way there to the surface. So that's the water. That's when the cable snapped. I'm ready to see. My initial velocity, I think we found it here, and I think it was negative 1,96. We just don't know the velocity when I hit the water. But I do know that it snapped 30 meters above the water, right? 30 meters above the water. Okay, fine. Now, if I consider this portion from here, where the initial velocity is 0, up to the water, then the distance from there to there for me was 0,2. And so the distance from where it snapped to the ground is 30 meters. So then this is 0,2, obviously, because it's coming to the same level, like this level. So from here, if I consider this portion from here up to here, the total distance traveled is 30 plus 0,2. And I'm going to use that equation, VF squared is VI squared plus 2G delta Y. And if I use this portion only, my initial velocity is 0, and G1 is positive, 9,8, and I'm going down is positive, that's 30 plus that's 0,2, and I'm looking for VF, I mean, I've got VF squared. Do your maths properly, 24,58 meters per second. That becomes your VF. You know why I picked this way? It's because if I use the other ways and I use 9,8, I'm not going to get 24,58. I'm going to get 24,3 something. And so I use this one here because I want it to be 24,58, just like what they did. But remember, guys, again, we can use the other methods and still get the proper answer. It's just that back then they were using 10. We are using 9,8. So your answer for VF becomes exactly that one. Remember, you need to square root it at the end of the day, and it's going to be a positive number because you will square root, and square root gives you plus and minus. Though your calculator gives you a positive number, but don't forget the plus and minus, and they say down is positive. They told me this time down is positive. So 24,58 meters per second. We're proving it using this method. The other way in which you could have done it, though you won't get the same answer if you use 9,8, is to simply say, okay, I started off with negative 9,6, right? And the total displacement of this object is actually 30, because this displacement here and here will be 0. So this one becomes the initial. It doesn't become 0 like what I had. This one becomes the initial. And then your final is what you're looking for, VF, which you don't know. Then the total displacement is 30. You're going to get a number if you use 10, exactly like this. If you use 9,8, which we're using, 24,3 something, I did this yesterday, I think. And still, the physics is the same. It's just that the problem with this one, it's a very old syllabus question. They were using 10 instead of 9,8. But basically speaking, that is your question. All right, guys, we've copied this down, maybe. Give you a couple of seconds. Oh, you've been wonderful, man. Thank you so much, family. You can do more of this. Practice makes perfect. I've been getting ideas about, okay, the user says, show us how you square root it. Oh, okay, right, that's a question. Let me show you. What I simply do is this. I get an answer for this. Somebody just sent a message to say, show us how you square root it. I just get an answer and just take my calculator, right? I get an answer for VF squared. That's what I do. I just get an answer for VF squared. And then this is 0 obviously. Then let me do my maths. 2 times 9,8 times that whole thing, which is 30 plus the 0,2, right? 30 plus 0,2 there. They are just times 9,8, okay, times the 2 there. Right, so I should get a number like 591,92. Then I square root it like this. Like that's pretty much what I do. And let me see if I get the answer. Square root of that. Yeah, I think I get 24, I get 24,33 if I use 9,8. Yeah, but if you use 10, and maybe it's because again I also rounded off with some numbers. If you use 10, you should be able to get the 24,58. You see, this whole thing of having 9,8 and 10 can represent a bit of a problem in terms of there's an offshoot of an answer in terms of just a couple of decimals, but it's not too bad. Like I said, guys, try to use 10 and see what you get. Try to use 10, see what you get. You're going to get the same answer like me. 24,058, I think. Try to use 10 and see how far you get. I think you should be able to get that, guys. Our time is really gone. I also have something to do now, but fine. Try to use 10 and see. See, for me, it's the logic of so someone says, why did you use 0? Say. Okay, okay, let me explain again. I used 0 because I was using this portion just from here to there. I was using this portion just from there to there, right? Just from there to, that's why I used 10. I used 0. But if I decide to use negative 1,96, then I'm just going to start here. Then I'm going to do this. Negative 1,96, negative 1,96. Then I won't use 30,02. I'll now use 30 because that's the total displacement traveled by the object. Again, this is our problem, 9,8 and that whole 10 thing. Get whatever answer you get, you're gonna get, I think 24, something. So the reason why I used 0 was just, I used this portion from there to there. But you can also use the whole portion up to the end. And if you use the whole portion, the total displacement is actually 30, not 30,2. Right, so it's just the semantics of math, the plus and the minus situations. That's all that it is in total. In essence, that's what it is. Okay, we've come to the end of our lesson. Thank you so much for your patience, and I think you guys have been wonderful. And I think you guys will get the best marks at the end of the day. Thank you to the Facebook family as well. Let me just check on you very quickly. There you are. I'm going to say goodbye to you. I'm going to stop the live. Let me just write my number for those that want, and I'm writing it on Facebook. And I'm seeing your answers, your questions now. I'm only seeing them. You ask me privately, I'll be able to help you out. I'm writing my number on Facebook so that people can be able to get the handout if you need the handout. I also do the same here on Zoom, just in case you want to get the handout or whatsoever. But otherwise, I'm going to stop the live feed on Facebook right now, then open up Zoom and we say hi and bye to each other. There. Facebook family, you guys have been lovely. Peace and out. I'm stopping the live feed.